Hello and welcome to our last lesson on optimization, as well as our last lesson for this unit. So today we are looking at the last category of our optimization problems, distance and time. And so our learning goal is to be able to solve rate of change problems involving distance, time, and motion using derivatives. So in our first example, we have motion under gravity. And as you read this, it should remind you of a lot of similar problems you've seen when working with quadratic functions. And you actually are able to solve this function completely using what you've learned with quadratics. But now we're going to see how derivatives can help us as well. So a baseball is thrown upwards and its position s of t in meters above the ground is represented by the following function, and t is in time is the time in seconds. So again, this is a quadratic equation. So our first part, we are asked to determine the maximum height the ball reaches. So this is actually the vertex of our graph. So using now what we know about derivatives, and maybe let's just do an image first. So given a motion such as this, where the ball is thrown upwards and it travels back down, this is the vertex, which is the maximum height. But at this height, we also have that the derivative is actually momentarily zero. So if we have a tangent line at this point, it will be a horizontal line. So now we're going to figure out what that point is using derivatives. And so that's exactly what we have written over here. At the maximum height, the ball reaches a velocity of zero. And so to find the time, we're going to start with the derivative function, which is v of t. And remember, s of t is our displacement function. So v is now our velocity. So this is also s prime of t. And we're trying to find at which values of t is this equal to zero. So by derivative rules, v of t, which is, again, s prime of t, is equal to negative 10, which we get from power rules, plus 30, and the 1 is a constant, so it does not contribute to our derivative. And this equals 0 when, and this is just rearranging, when t is equal to negative 30 over 10, which is 3. So at time 3 seconds, because our time was in seconds. And we're at the maximum height the ball reaches. So we have the time, and now we just substitute back into our s of t function to get s of 3 is equal to negative 5 3 squared plus 30 times 3 plus 1, which is 46 meters. And don't forget your concluding statement, the ball reaches a maximum height of 46 meters. Now the next part, we're asked to determine the velocity of the ball if it was caught at 1 meter above the ground. And so just analyzing our function here, we know that at s of 0, so at time 0, this is equal to 1 meter. So one interpretation right away is that the ball was thrown at from a height of 1 meters, or 1 meter. So now, for the ball to be caught at 1 meter, then s of t is equal to 1. And now we're just solving, and this is just, you can do factoring here. So s of t being equal to 1 means that this expression is equal to 1. But again, the ones are canceled out. So we have negative 5t squared plus 30t is equal to 0. And taking the square root, we have, factoring, we have t is equal to 0 and 6. And the factoring would just be take t, actually, we would take negative 5t. So then we're left with t minus 6. And so for this to be equal to 0, we can either have the t is equal to 0 or t is equal to 6. And again, this is what that interpretation that we had from the beginning. So at time t is equal to 0, the ball is thrown in the air. So this value does not actually satisfy our condition because you can't catch the ball at that time because it's just being thrown into the air. So we would say this value is inadmissible in our context. And so we actually only look at that t is equal to 6 value. And so when t is equal to 6, the velocity is, and that's what we were asked to determine the velocity. So we substitute into our velocity equation or our derivative function, and we get negative t times negative 10 times 6 plus 30 is negative 30 meters per second. And don't forget your units here. With velocity, it is meters per second. And now we're asked, why is the velocity negative here? And so again, consider this motion where we are going up at the maximum height, and the maximum height was at time is 3. And so let's say this is the point 1, uh, sorry, 0, 1, which is when the ball is thrown into the air. Then this point is 0, or sorry, 6, 1. And this is just the symmetry of our quadratic graph. And so as the ball is coming this way and we're catching it, this is moving downwards. In our displacement, we were considering the upward motion as our positive. So as we're going up, that's the direction that we're throwing the ball in. And then as the ball is coming back down, that's our negative value. So that's why we have a velocity of negative 30 meters per second, because we're saying that we're moving in the opposite direction. And then the speed is 30 meters per second. And that is it for that question. Moving on to our example 2. So here we're told that Isabel and Alec are both training for a marathon. Isabel's house is located 20 kilometers north of Alec's house. At 8 a.m. one Tuesday, Isabel leaves her house and jogs south at 8 kilometers per hour. At the same time, Alec leaves his house and jogs east at 6 kilometers per hour. And we're asked, when are Isabel and Alec closest together? Given that they both run in the same direction that they continue in the same direction. So Isabel, who's running south, continues running south. She doesn't change direction. And Alec, who's running east, will continue to run east for 2.5 hours. And this is now our restriction for one of our variables, which is time. And our other variable is the position of both Isabel and Alec. And so again, this is one where it's really important to draw a diagram. So let's interpret our diagram here. So this is Alec's house, and Isabel's house is 20 kilometers, and should be kilometers here, 20 kilometers north of Alec's house. So we have north, south, east, and west. And so Isabel leaves her house and she starts jogging this way. She's going this way. And Alec leaves his house and he's jogging east this way. And so eventually, at one point, Isabel will be at point J and Alec will be at point B. And we want to know at which is this distance minimized. So we have they are the closest together because the distance between them is the least. So this is just that interpretation right here. So Isabel starts at point I, that's her house, and jogs south at a speed of 8 kilometers per hour. And so she will reach point J after T hours. And so IJ, which is where she's going to end up, is 8T kilometers. So kilometers per hour times the T, which is hours. And so JA is going to be 20 minus 8T. And this is just the distance, so we're only working with distance here, so it's in kilometers. Now, Alex starting at point A, he's jogging east at a speed of 6 kilometers per hour. So he will reach point B, and after T hours, this will be represented by 6T, which is his speed times the time, and that will give you the distance, or the distance that he's traveled. So how can we use this information to find the distance between Isabel and Alec? And I've already given you an interpretation of it, but how can we do this now using math? So again, because they were both running at the same time, then the distance between them is given by the variable T after T hours. So the T is in common for both of them. And so we can now define a new variable, which is S of T, and this is going to be the distance between point J and point B. And it's also the line JB. So this distance, and this is just because we're working with north and east, this is a right angle. So we are using Pythagorean theorem here to find S. So using Pythagorean theorem, we know that a squared plus b squared is equal to c squared. So that means JA squared maybe let me write this for you. S of t is S of t squared is JA squared plus AB squared. And going back to what I had here, we had AB, we also had JA. So now we're just substituting to create our function for S of t. So this is 20 minus 8t squared plus 6t squared. And because we only want S of t, we do take that square root as well. And so expanding and simplifying, you should get, and double check this for yourself, 100t squared minus 320t plus 400. And I'm just rewriting this with an exponent of half. And the reason I do this is because we're working with derivatives. So having that, I can apply the power rule and then the chain rule for the polynomial that's inside the bracket. So again, our variable here is t, and we do have a function given in one variable, which is what we wanted to begin with. And so, considering the restriction at t, we have the t is between 0 and 2.5 because that's what we were told. They are running for 2.5 hours. And so we consider both the time at which they start, so they're in their own homes, and then as they continue to jog, we go until the other endpoint, which is 2.5 hours. And that's exactly here. And with time, we can have inclusive because perhaps if one of them is running really fast, the closest time is when they are starting and they're just at their houses, which is that 20-kilometer distance. And so exactly, yeah, why do we consider the endpoints? T is equal to 0 and t is equal to 2.5. Again, it's because in this context, we do have S of t defined for those values, and it would make sense. They could be our the values for which the distance between Isabella and Alec is the least amount of distance. So now finding the derivative function, I'm applying M power rules. I have half there, and then I just keep my square root, but then we have minus 1 there, so we end up with negative 1 over 2. And then 200t minus 320 is the derivative of this quadratic function here because we have to do chain rule. And so rewriting this, and what I've done here is just factor out a 2 from here, and I was able to simplify with this 1 over 2. And so I have 100t minus 160 from here. And this is just this square root, but I took the negative away and I wrote it as a square root in my denominator. So now I encourage you to try finding the different values for our critical point, which is when S prime of t is equal to 0, as well as for the two endpoints. So S prime of t is equal to 0. This one's pretty simple because we had, for this to be 0, we are just considering the numerator to be 0. So 100t minus 160, we have that t is equal to 1.6. So again, try to find what the distance is at each of these points. So you should get that S of 0 is just 20 kilometers, and that makes sense, right? When they're both at their houses, they're 20 kilometers apart. At 1.6, this is 12 kilometers. And then finally, at time is 2.5, they are 15 kilometers apart. And so going back to our graph here, so perhaps this is time 1.6. And so this distance would be 12 kilometers. And then as they continue to jog, Alec is still getting further and further. So even though Isabel is getting closer, Alec is like all the way gone. And so the distance is now increased to 15 kilometers. So the minimum value of the distance between them is 12 kilometers, which occurs at time 1.6 hours. And you can do a further step here to try to write it in terms of hours and minutes, but this would also be sufficient because we were told our unit is an hour, so I can just stick with that. Now, our next problem we have, a man lives on an island 1 kilometer from the mainland. His favorite restaurant is 3 kilometers along the shore from the point on the shore closest to the island. The man can paddle his canoe at 3 kilometers per hour and can jog at 5 kilometers per hour. And we're asked to determine where he should land if he's canoeing so as to reach the restaurant in the shortest possible time. So we want to have a function that would tell us the time. And so let's start with our diagram. And I do have this additional information here for you as well, which we will use shortly. But for a diagram, suppose this is the island and the man is on this island, and this is now the shore. So he lives 1 kilometer from the mainland. So that's actually also the point on the shore closest to him. So we can let this be point C, and I've defined my variables here for you, but I'm just letting you know now here from the diagram, and then I've defined them below. So C is the point on the shore that's closest to the island. And again, this is 1 kilometer. And then we define also R, which is the restaurant. And finally, we define this new point P, which is a potential point where he can land. So he can choose to canoe all the way to point P and then go to the restaurant from point P. And we were also told that the restaurant is 3 kilometers along the shore from the point that's closest to him. So from point C to the restaurant R, this is 3 kilometers. And so this is also right triangle here because, again, remember closest distance is the horizontal line. So that's why we have a right angle there. And so we can define this distance to also be x. So the distance from the closest point to the point that he lands at. And this is going to help us now create a function in terms of one variable because we have x here, and this would be 3 minus x kilometers. And so again, yeah, I've defined my variables here. So I is the island, C is the point closest to the island, R is the restaurant. And now let P be the point at which he lands. And this is X kilometers away from C on the shore. So he has three options here. And I'll just go back here to show you visually. He can just go directly to the closest point with his canoe and then jog all the way to the restaurant. He can also just directly paddle to the restaurant with his canoe and do no jogging. But because he wants to find the fastest time, so he might go canoe to this point P and then jog all the way, the rest of the way to the restaurant. And this is actually our two endpoints, which is going to C directly or going to the restaurant directly, or our critical point here, which would possibly give us a faster time than either of these endpoints. So now is where I'm going to also use what I have here. So speed is distance divided by time. So S is equal to D over T. So again, we have X is the distance from the closest point at which he will land. And I've already mentioned this to you, but which two options is considering the endpoints? So either that he's going directly to the closest point C and jogging the rest of the way, or he canoes in a diagonal path directly to the restaurant. So based on that, we also have this restriction where X is between 0 and 3 inclusive because we are considering those endpoints of him going directly to point C or going directly to point R. So now, considering this triangle here, CPI, we have X here and we have 1. So we want to know what this distance is, which is also the distance at that he will be canoeing. So this is now Pythagorean theorem. So the distance that he canoes or paddles is given by IP, which is square root of 1 plus x squared. And the distance that he jogs is the remaining distance from point P, which is also 3 minus x. So he canoes this distance and he jogs this distance. So now we have the function of his time given the variable distance here. So our function is t of x and t for time, and this is the time he will canoe, which we get by adding the time for which he canoes and the time that he will travel, which is given by the time that he will go on the canoe as well as the time that he's going to be jogging. And these are both dependent on his speed for canoeing as well as his jogging speed. So time is distance divided by speed here, and distance is the quantity that we define, so our variable, and speed we were given. So this is the distance which he canoes, and he canoes at 3 kilometers per hour, so that's why we divide by 3. And then the distance that he jogs is 3 minus x, and we divide by the speed, which is 5 kilometers per hour. And um, so one interpretation of this could be maybe the water is not very calm, so maybe it takes him longer to canoe. That's why his speed is less than if he was jogging. Now, I have a function t of x with one variable. So to find the least amount of time it takes, we are finding the point at which the derivative is equal to 0, which is that critical point. So I just rewrote this a little bit nicer. So here I just gave my square root as a power again because I want to use power rule. And then 3 minus x over 5, I just split this up into 3 divided by 5 and then minus x divided by 5. And the reason I did that is because now I can use difference rule for derivatives instead of having a quotient rule here. And I can do this because this is a constant, so it's a lot easier now. So now I suggest try using derivative rules to differentiate this function. And you should get t prime of x is given by this this expression here. So the half is that power, and now we have negative 1 over 2 for our power here. 2x is the derivative of this internal function, so chain rule there. And the 3 over 5 was a constant, so it does not contribute to our derivative. And then finally, this negative x over 5 gives us negative 1 over 5 because dx by dx is just 1. And now I'm going to move this square root to my denominator, so I have, again, a nicer looking expression because now I'm actually going to be using this to solve. So setting t prime of x to 0, we are solving for x. So this is a binomial, so then I can just set these two terms to be equal for the t prime of x to be 0. And I would get 5x is equal to 3 times square root of 1 plus x squared. This is just the butterfly method. And squaring both sides now, because I want to get rid of this square root here, we get 25x squared, which is equal to 9, because this is outside of the square root, so it does get squared, and then 1 plus x squared, so the square root is now gone. And now, expanding this, distributing this, and then simplifying, I have 16x squared is equal to 9. And so, solving from here, x squared is 9 over 16. So x is plus or minus 9 over 16, and this is just 3 over 4. So x1 is positive 3 over 4, and x2 is negative 3 over 4. But consider again, we have this restriction of x has to be between 0 and 3. So we're not going further away from the shore, which is what this negative value would tell us. So we only have one admissible solution, and it is 3 over 4. So he should land 3 over 4, or 0.75 kilometers from the closest point on the shore to get there in the fastest time. So for example, consider that he would he would canoe all the way here, and this distance is 0.75, so we can also use Pythagorean theorem to determine the distance that he canoes, and this distance here would be 2.25 kilometers, and that's the distance that he is jogging. And now I want you to consider, why is the shortest path not the fastest path? So the shortest path would be him going directly to the restaurant, right? Which we know from properties of triangles, that would be our shortest path, but that is not actually giving us the shortest amount of time. And you can double check this for yourself to determine what t of 0 and t of 3 would be. And maybe take a moment and try to solve those. So I also added that t of 0.75 because, again, we do want to be considering those endpoints as well as our critical point here and finding those outputs to really finalize our answer. So if you do that, you get 0.93 for time t of 0. And then for our critical point, we have 0.87 hours. And then for t of 3, we actually have the slowest time, which is 1.05 hours. And again, the reason for this is consider his speed, which when he canoes, it's 3 kilometers per hour, and when he jogs, it's 5 kilometers per hour. So when he's jogging, he's actually faster. And as you can see, if he decides to just canoe straight to the to shore and just jog all the way to the restaurant, he actually has a faster time than if he canoes to the restaurant, which would take him 1.05 hour. And it is because his speed is faster when jogging. But of course, in real life context, we have other factors to consider. For example, if he's jogging all the way, he might be more tired. He may have a preference to not be jogging, and he may choose to go with the shortest path, which gives him a longer time. But at least he's not jogging; he's just in his canoe. So. Um, there in real life context we do consider different factors, but for this problem we were just asked what's the shortest or which path gives him the shortest time, and so we see that it is at x is equal to 0.75, which is 0.87 hours. And for our final example today, and I wanted to show you a trigonometric function here as well. So a particle moves along a line such that its position is represented by s of t is equal to 8 sine 2t at time t. And so I didn't really give you a unit here for time because we are also considering just a particle. I just wanted to show you what it would look like with trigonometric functions. You typically don't really use trigonometric functions in optimization problems. It's not very common, but because we've seen it in our derivatives, I did want to include this example for you as well. So given that t has no unit, you can just use t units. And then any unit interpretation that we have here, whether we say it's seconds, hours, minutes, then we can just replace units with the given unit. So we're asked first, for what values of t does the particle change direction? So consider it's this in its displacement, and it's moving, for example, upward, and then it changes direction and it goes downward. Or if it's going to the right, it changes direction and now it's going to the left. And remember, when we are changing direction for a very brief moment in time, so our instantaneous rate of change will be 0. And again, it's instantaneous. It'll be very quick, but it will be 0 nonetheless. So we are trying to find the velocity, because again, this is a displacement function, and we're trying to find at what time is that velocity equal to 0. And that would give us also when the particle is changing direction. And consider, because this is also a sine function, and always try to add some like knowledge that you have, background knowledge that you have before even solving the problem. We know that sine functions have a cycle and they repeat. And so we can assume the particle is just moving, for example, right and left, right and left, right and left, or up and down, up and down, up and down. And so this one actually will give us multiple values of t, not just one value here. So solving first for the derivative function s prime of t, we have that this is equal to 8. This is our constant multiple. And then 2 cosine of 2t. And the 2 here comes from 2t because this is a chain rule. And the derivative sign is just cosine. So that's why we have cosine of 2t. And then again, this 2 is from chain rule. And so just simplifying this now, this is written as 16 cosine of 2t. So now we are using what we know about trigonometric functions. So we know that cosine is equal to 0 when we have pi over 2, 3 pi over 2, 5 pi over 2. And as a general rule, pi over 2 plus k pi, where k is an integer. So if k is 1, we have this case. If k is 2, we have 5 pi over 2, and so on. And although we're not given a unit for t, we still do want to acknowledge that t is greater than or equal to 0 because we cannot have negative time. But we were told that this is cosine of 2t. So really, it was 2t that is equal to all of these. And so we want to know what value of t we have. And so that's what I've done here. t, and this is just dividing all of these values by 2. So pi over 4, 3 pi over 4, 5 pi over 4. And again, as a general rule, we have pi over 4 plus k pi over 2. And this is exactly what I had here, but I've just divided both of these terms by 2. And this is an integer k. So the particle then, we can say, changes directions at times t is equal to pi over 4 plus k pi over 2 for an integer k. So it's not actually a specific or exact value you're giving, but you're giving an answer that we can find all the different, again, because it's a cyclic function, all the different values that it is changing direction at. So perhaps here, 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 and so on. And also, one thing to point out here as well. So we are actually changing directions both when we are going now. So for example, if we're starting to go up and now we're going down, you have a change of direction here, but you also have a change of direction when you're going down and then you suddenly go up. So that's why we consider all of those values. So this would be pi over 2, 3 pi over 2, but then because it's 2t, this would be pi over 4, 3 pi over 4, 5 pi over 4, and so on. And so that's exactly what I've done here. So I just did the division by 2. So all the terms that were originally here, they are now divided by 2 to get the denominator of 4. And then for my general term, which is pi over 2 plus k pi, we now have pi over 4 plus k pi over 2 for an integer k. So next we're asked, what is the particle's maximum and minimum displacement from the starting point? So again, the maximum, for example, if it starts at t is equal to 0, we know that because of sine function, it is the displacement is 0. So then it moves up a certain amount, and then it changes directions and goes back down and then moves up and so on. And so we are considering now the displacement at those turning points, and because of the 8, we have 8, negative 8, 8, negative 8, and 0. And we only consider the interval 0 to pi because if it works here, it's going to apply for throughout our function. And so the displacement from the starting point, we see that we either go up by 8 or again from the starting point, we go down by 8. And so the displacement here doesn't necessarily need a direction. We can just say it is 8 units. And again, this one is a special word problem because I didn't give you any units in it. So we are just working with 8 units here. Again, I just wanted you to see what a application question would be like with sinusoidal function. So we could add any units here and it would still work. And finally, we're asked, what is the particle's maximum velocity? So here we're just doing a little bit of interpretation. So again, we can only just check for the interval 0 to pi. But now we're asked for velocity. So we're checking the s prime of t function here. And so that's our cosine. So we know cosine has a maximum when x is equal to 0 and 2 pi, and so on, like 4 pi and so on, and a minimum at pi, 3 pi, 5 pi, 7 pi, and so on. So then cosine of 2x has its maximum at x is, and again, I'm just thinking if it's x is these values, then what do they have to be for 2x? So it's 0, pi, 2 pi, which if you do 2 times each of these, you get 0, 2 pi, 4 pi, and so on. And the minimum, again, same thing. I'm just dividing these values by 2, so we get pi over 2, 3 pi over 2, 5 pi over 2, and so on. And again, because we're at the maximum velocity, so we don't consider the direction, we only consider the speed here. And I mean, even if we are considering velocity here, it would be the positive motion. So 16, and again, no units here. So that would be our final answer here. And so I hope you got like a bit more knowledge seeing now a trig function with optimization. And that's a wrap on our lesson as well as our unit. So you have some practice problems here. Make sure you're practicing those. And as always, if you have any questions, don't hesitate to reach out, and I'll see you all next class.